Hi, I'm Jake Rankin. I'm the head laser technician here at Wisconsin Engraving, and I'm going to be talking about laser texturing technology. The company we get our laser texturing technology from is GF Machining Solutions. In order to explain laser texturing technology, we're going to show you a video from GF. This video is a short explanation of how their laser technology works. GF makes a couple different kinds of lasers. Nanosecond and femtosecond just refers to laser pulse duration, but the one we have here at Wisconsin Engraving is a nanosecond laser. The laser source is in the back of the machine. The laser beam is directed from the source all the way through the machine and out the laser head. Inside of the laser head is a couple of small mirrors called galvo mirrors, which are used to direct the beam along a path. It is important to remember that laser texturing is a digital process. GF has a good outline for the digital process workflow, which you'll see in this next clip. They go over it pretty quickly here, so I'm going to give a more thorough explanation for each of these steps. So, we're starting with step 1, importing the 3D model into Rhinoceros 5.0. Once imported, the model has to be carefully placed. We are working off the center of the block for this one, so that's where our 0 has to be. The steps are a little out of order, but that's alright. We're moving on to step 3, selection of the area to be textured. Through the 3D model and carefully selecting the surfaces that need attention. This takes a little bit of time, so we'll just speed through it. The surfaces are selected, everything is joined and organized, and then we can move on to the next step. Alright, we're on to step 2, the meshing process. 4 are selected and converted into a mesh. The box on the right here is GF's laser design application. It functions as an add-on to Rhino. It includes some tools for checking the mesh's compatibility with the post-processing that eventually must happen. Repairing a mesh takes a while, and this can be one of the longest steps. has been fully repaired and we're certain it's compatible with the laser design software, it can be exported for use in the next step. On to step 4, the mapping process. The application being used here is called Unfold 3D. This software is used for UV mapping the mesh. It is able to unfold the 3D geometry and flatten it out so that a texture can be applied. After mapping is done, the mesh is exported along with all its mapping information, giving us a mesh that is ready for the next step. Step 5, Texture Application. This is where we transition into Adobe Photoshop and Illustrator. This part needs a border around the parting line. Fortunately, the previous step gave us some files that can be used to easily add a border around the edges. After the border is done, we export a TIFF file and move over into Photoshop. In Photoshop, the texture area is selected and filled with a grayscale pattern. GF's laser design software works from grayscale TIFF images. The levels of grayscale in the image are translated into depth of cut with laser design. Black pixels are engraved to full depth, while white pixels have no depth. The UV mapped mesh from Unfold 3D is imported back into Rhino. Then, the texture image from Photoshop is loaded into the object. And we just have to switch to a rendered preview to double check the border area, and it's ready to post. Toolpath, patch, and machine configuration are set, and we can start posting. The orange mesh here is an anti-collision mesh. It is necessary for posting in order to make sure the block does not interfere with the path of the laser. After posting, there's an application that GF provides called the Laser 3D Toolpath Viewer. This allows us to look at the toolpathing that laser design outputs. Being able to see the toolpath lines gives a better idea of how the laser actually works. The way this machine tool works is no different than any other CNC out there. A tool is traced along a path at a defined speed in the appropriate direction, with deeper cuts being made in passes over the same area. The tool on this machine just happens to be invisible, since it's a laser. Everything looks pretty good here, so we're on to the next step. Step 6, 5-axis simulation time. Simulating the posted program requires an anti-collision mesh. This mesh is made from the block that is going into the machine, and it has to be positioned properly for use in the simulation software. After making the mesh in Rhino, it is exported for use in GF's anti-collision software. The machine, part, and program are loaded into the simulator. The offset is selected and the program is run. Simulating the program helps avoid crashing the machine. Step 7. 5-axis machining. The laser we have here at Wisconsin Engraving is an LP1000U, and it looks kind of like this. The control desk is on the right. Opening up the doors at the front of the machine, the table where the part goes looks like this. So we load the block in and begin to set up the object reference. A total of 7 points needs to be picked up with a probe so the machine knows the position and orientation of the block. We duct taped a GoPro onto the head so you can see the laser at work. After getting the object reference set up, a short, low-power paint removal program is run to make sure everything will go alright during the high-power texturing ablation. Alright, so after the paint removal is finished, the part must be carefully inspected to make sure the laser is hitting where it's supposed to. After everything checks out, the texture program can be run. The texturing took about 3 hours on this part, but we'll speed through it here in about 3 minutes. Thanks for watching.